Good morning. So in the last class, we discussed about the Firefighter techniques. Those are Fourier series method. Second one is Windows method. In Windows method, we have some 4 to 5 methods are there. That is Kaiser method, Kaiser Windows technique, and and Windows technique and Windows techniques. Like that, 4 to 5 methods are there. Okay. So and the third one is frequency sampling method. Okay. How to design this frequency sampling method. So we'll see design of FIR filter by frequency sampling method. That is here the procedure is like this. Procedure for type 1. So first point is we have to choose the ideal frequency response or desired frequency response HD of e power j omega. Okay. Sample HD of e power j omega at endpoints by taking omega equal to omega k equal to 2 pi k by n, where k equal to 0, 1 to up to n minus 1. Okay, to generate the sequence h bar of k. So h bar of k is nothing but a hd of e power j omega at omega equal to 2 pi into k by n. Right? 2 pi k by n. So compute the n sample of h of n using the following equation. That is case 1. Here we will take 2 cases. If n is odd, n is even. Suppose if n is odd, then h of n will become 1 by n into h bar of 0 plus 2 times of the sigma k equal to 1 by n minus 1 h bar of k into e power j 2 by kn by n. Similarly, for case 2, if n is even, then h of n will become 1 by n into by h bar of 0 plus 2 times of sigma k equal to 0 to n by 2 minus 1 into real part of h bar of k into e power j 2 pi into k by n. So now take the transform of the impulse response of h of n to get the transfer function of h of z. So h of z equal to sigma n equal to 0 to n minus 1 h of n into z power minus n. So h bar of k is equal to magnitude of h of k. That is h of k into e power j theta. For linear phase filter, theta value is minus alpha into omega, but theta equal to minus of n minus 1 by 2 into 2 pi k by n, or theta equal to minus of n minus 1, 2 gets cancelled, minus of n minus 1 by n into pi k, where k equal to 0 to n minus 1. Okay, so the filter quotient h of n can be obtained by finding the inverse discrete Fourier transform of h of k. So that is h of n equal to formula for inverse discrete Fourier transform of h of k. That is h of n equal to 1 by n into sigma k equal to 0 to n minus 1 h of k into e power plus j 2 pi k n by n, where n equal to varying, n is varying from 0 to n minus 1. Okay, if h of n, the impulse response of the filter, to be real valued system, the frequency samples h of k must satisfy the symmetry requirement for n odd or n even. So h of n minus k will become h star of k, where k is varying from 0 to n minus 1. So in addition for n even, in addition for n equal to n is even, so h of n by 2 is equal to 0. With the frequency response h of k, the magnitude response is an even function. That is mod h of k is equal to mod h of n minus k, where k is varying from 0 to n minus 1. So the phase is an odd function. We represent phase function theta of k is equal to minus of theta of n minus k. This is an odd function, whereas magnitude is an even function. Okay, so theta of n minus k equal to minus of n minus 1 by n into h of n minus k. Phi of n minus k, that is minus of n minus 1 by n into phi into n minus phi into k. So it is equal to minus of n minus 1 by n into phi into n plus minus of n minus 1 by n into phi into k. So n gets cancelled. So it will become minus of n minus 1 into pi plus n minus 1 by n into pi k. Okay, so theta of k for n is odd is given by theta of k equal to minus of n minus 1 by n into pi k, where k is varying from 0 to n minus 1. So multiply this one. So n minus 1 minus 1 by n. So n minus 1 into 5 minus n minus 1 by n into 5k, for k equal to n plus 1 by 2 to n minus 1. Okay. So theta of k for n even is given by theta of k equal to minus of n minus 1 by n into 5k, where k is varying from 0 to n by 2 minus 1, or it is equal to 0 for k equal to n by 2. Okay. So it is n minus 1 into 5 minus n minus 1 by n into 5k for k equal to n by 2 plus 1 to n minus 1, or theta of k equal to minus of theta n minus k. For n is odd, h of k equal to mod h of k into e power minus j n minus 1 by n into 5k for k equal to 0 to n minus 1 by k, or it is equal to h of k mod h of k into e power plus j into n minus 1 n minus 1 into n minus 1 into 5 minus n minus 1 by n into 5k for k equal to n plus 1. This is 5k. For k equal to n plus 1 by 2 to n minus 1. For n is even, h of k equal mod h of k into e power minus j n minus 1 by n into 5k, where k is varying from 0 to n by 2 minus 1, or it is equal to mod h of k for k equal to n by 2, and it is mod h of k into e power j n minus 1 into 5 minus n minus 1 by n into 5k for k equal to n by 2 plus 1 to n minus 1. For n is odd, h of n equal to this one by n into sigma k equal to 0 to n minus 1 h bar of 0 plus 2 times of sigma k equal to n by 2 n by 2 minus 1 into real part of h of k into e power j 2 pi n k by n. For n is even, h of n equal to 1 by n into h bar of 0 plus 2 times of sigma k equal to 1 to n by 2 minus 1 real part of h of k into e power plus j 2 by n k by n. So once the filter quotient h of n have been determined, system function filter is given by h of z equal to sigma n equal to 0 to n minus 1 h of n into z power minus n. This is z transform. Okay. So by doing that, we can get the h of z. So now determine the filter quotient h of n obtained by sampling hd of n equal to hd of j omega is equal to e power minus j n minus 1 into omega by 2, for 0 is less than or equal to mod omega is less than n by 2, and is 0 for pi by 2 is less than or equal to mod omega is less than or equal to pi, for n is 7. So here the solution is wk equal to 2 pi into k by n, where k equal to 0 to n minus 1, h bar of k equal to h of k or mod h of k into e power j theta into k. Wk is equal to 2 pi into k by n, where k is varying from 0 to 6. Okay, if k is 0, then w of 0 becomes 0. If k is 1, w of 1, w1 equal to 2 pi by n. 2 pi by n, here n is 7, that is 2 pi by 7. Okay. Next, if k is 2, then it is 4 pi by 7. N is 3, it is 6 pi by 7. N is 4, it is w4 equal to 8 pi by 7. N is 5, it is 10 pi by 7. And n is 6, it is 12 pi by 7. Okay. So these are the values. 0.28, 0.57, 0.857, 1.14. So with these values, you can draw the plot. So h of mod h of k versus k, mod h of k versus k. Here mod h of k is c e power minus j into n minus 1 into omega by 2. Okay, h of e power j omega, if k equal to 1, then it is 2 pi by 7. So mod k equal to mod of h of k equal to 1, then k equal to 0, 1, 6. It is equal to 0 for k equal to 2, 3, 4, 5. Depending upon this equation from 0 to 5 by 2. From 0 to 5 by 2. So from 0 to 5 by 2. 5 by 2. Its value is like this. 0 to 5 by 2. Okay. So it is 0, k values are 2, 3, 4, 5. Okay. So n is even, then theta of k is equal to minus of n minus 1 by n into pi k, where k is varying from 0, k are 0, 1, 2, 3. Okay, that is n is 7 minus 1, that is 6 by 7 into pi k. Here k equal to 0, 1, 2, 3. If it is odd, n is odd, then theta of k equal to n minus 1 into pi minus n minus 1 by n into pi k. So it is n minus 1, that is 6 pi minus 6 pi by 7 into k. So here k values are 4, 5, and 6. So h of k equal to h paint equal to theta of k, or h of k equal to 1 into magnitude is 1 into e power minus j 6 by n minus 1 by n, that is 6 by 7 into n for k equal to 0, 1. It is 0 for k equal to 2, 3, 4, 5, and it equal 1 into this one for n k equal to 6. If n is odd, you can calculate this. So that is h of n equal 1 by n into pi of k of the h of 0 plus 2 times of this. Okay. Simply substituting, we can get h of n equal to 1 by 7 into 1 plus 2 into cos 2 pi by 7 into n minus 3. Now h of n equal to h of n minus 1 minus n, that is 7 minus 1, 6 minus n. Okay. So by simply substituting these values, we can get h of 0, h of 1, h of 2, h of 3 like this. Using frequency sampling method, design band pass filter with the following specifications: sampling frequency of equal to 8 kilohertz, and cutoff frequency FC1 is 1 kilohertz, FC2 is 3 kilohertz. Okay, determine the filter coefficients n equal to 7. Okay, so we can start with the formula Wk equal to 2 pi by k by n. So W0 is 0, k is 0. Okay, so these are the values. And W7 equal to 2 pi into FC1 by Fs. Okay, so FC1 is given as 1000 FC, and F is given as 800, 8000. So 2 pi into FC1 by Fs. So 2 pi into 1000 by 8000, that is pi by 4. Similarly, WC2 equal to 2 pi into FC2 by Fs, that is 3 pi by 4. So mod h of k equal to 1 for k is 1256, and it is equal to 0 for k equal to 0, 3, 4. So theta of k equal to minus of n minus 1 by n into pi k. So k equal to 0, 1, 2, 3. And it is equal to minus 6 by n minus 1 is 7 minus 1, that is 6 by 7 into pi into k for k equal to 0, 1, 2, 3. So theta of k equal to n minus 1 into pi minus n minus 1 by n into pi k for k is 4 by 6. So it is 6 pi minus 6 by 7 into pi k for k equal to 4 by 6. So h of k equal to h of k into e power j theta into k. If h of k is 0 and it is 1 for the values, it is 1 for these values. For k is 5 and 6. So h of n, you can calculate h of n. And after that, h of n can be equated to h of n equal to h of n minus 1 minus n. So that we will get the values. So that is about the frequency sampling method. Okay. Then we will see the structures for realization of FIR systems. Okay, these are the different structures. In IAR systems also we have different structures. Okay, and here also we have the different structures. The different types of structures for realizing the FIR systems are direct form realization. Second one is transposed form realization. Third one is cascade realization. Fourth one is lattice structure realization. And the last one is a linear phase realization. Okay. Okay. So direct form realization of FIR system. Now we will see the direct form realization of FIR system. Finite impulse unit impulse response system. Okay. The direct form structure can be obtained from the general equation y of z of the FIR system as y of z is equal to sigma k equal to 0 to n minus 1 bk into z power minus k into x of z. Okay, bk into z power minus k. So k is 0, that is b0 into z power 0 is 1. So x of 0, that is x of z. Okay, x of z. Right. If b is 1, b1 into z power minus 1 into x of z. Similarly, b2 into z power minus 2 into x of z up to bn minus 1 into z power minus of n minus 1 into x of z. So, in general structure can be arranged like this. So, x of z into b naught, x of z into b naught plus x of z into z power minus 1 into b1. Okay, these two are added plus z power minus 1, or this is z power minus 2 into b2 into x of z. Okay, plus dash up to z power minus 1 into z power minus of n minus 1 into bn minus 1 into x of z. So we'll get the y of z like this. Okay, now relate the second order FIR system y of n equal to 2 into x of n plus 4 into x of n minus 1 minus 3x into 3x of n minus 2 using direct form structure. So y of n is given as 2 into x of n. Okay, plus 4 into x of n minus 1 minus 3 into x of n minus 2. Okay, by taking Z transform for this one, we will get y of z equal 2 into x of z plus 4 into z power minus 1 into x of z plus 3 into z power minus 2 into x of z. Right? So this is x of z into 2 plus z power minus 1 into x of z into 4 plus x of z into z power minus 2 into 3 minus 3. So that we will get y of z like this. So, or we can write this as x of z into 2 multiply x of z into 2 will be added to z power minus 1 into x of z into 4 and z power minus 1 into z power minus 2 into x of z into minus 3. It all will be added so that we will get y of z. Next one is lattice structure realization of FIR systems. Lattice structure realization. Okay, so the lattice structure consists of two different paths through which the input x of n is path through which the input x of n is processed. Hence, the lattice structure has two different output setups, that is y of n and y dash of n. Okay, it is looking like some flip-flop. Okay, so y of n is the real output and y dash of n is the supporting output. Okay, which offers the supports for obtaining the output for the next stage. A single stage lattice structure shown in the following figure, wherein K is reflection coefficient. Okay, suppose if y of n is given as x of n plus k1 into x of n minus 1, then it can be, and similarly y dash of n is equal to k1 into x of n plus x of n minus 1. It is represented like this. This is x of n, so this is the 4 minus 1. Okay, so and this is k1. K1 will be connected to here, and this is also k1 will be connected to here. So y1 of n equal to x of n plus k1 into x of n minus 1. This is just 4 minus 1. So y1 dash of n is equal to k1 into x of n plus x of n minus 1. Okay, x of n minus 1. This is lattice structure realization of FIR system. Then procedure to realize the lattice structure of the FIR system is like this. Okay. See the procedure. If the quotient of the present input x of n is not unity, convert it to unity by taking common of the quotient of the present input. Okay, so first of all, we have to maintain the quotient of the present input should be unity. Next, find the order of the difference equation and compare the quotient of the given difference equation with the quotient of the same order lattice structure output involving the reflection quotient k1, k2, k3 up to kn. Okay, find the order of the difference equation and compare the quotient of the given difference equation with the quotient of the same order. Okay, so lattice structure output involving the reflection quotients k1, k2, k3, k4 up to kn. Okay, and assign the calculated values of k1, k2 and up to kn, and construct the structure. Okay. Now we will see a problem. Realize a system with 6 into h of z is equal to 5 plus 3 into z4 minus 1 by using lattice structure. Okay, so 6 into h of z. Then we will write the h of z expression from this equation. H of z equal to 5 plus z power minus 1. Okay, then h of z is nothing but y of z by x of z. Y of z by h of z equal to 5 plus 3 into z power minus 1. So this is h of z is given as 5 plus 3 into z power minus 1. Okay, so y of z is equal to 5 into x of z plus 3 into z power minus 1 into x of z. Then y of n equal to 5 into x of n plus 3 into x of n minus 1, right? So 5 into x of n plus 3 by 5 into x of n minus 1. Okay, so y1 of n equal to x of n plus k1 into x. It is in the form of x of n plus k1 into x of n minus 1. Here k1 is 3 by 5. 3 by 5. Okay. So x of n into 5. So y1 of n equal to 5 into x of n plus 3 by 5 into x of n minus 1. So k1 value is 3 by 5. Okay. So 3 by 5 into x of n minus 1 will be added to 5 into x of n. Okay. Right. So like this, you can do the lattice structure problem. Next we will see the two-stage lattice structure. So how can we do the two-stage lattice structure. Yes, the output from the second stage of the lattice structure, which is the second order FIR system, is given as follows. Y2 of n is equal to y1 of n plus k2 into y1 dash of n minus 1. Similarly, y2 dash of n is equal to k2 into y1 of n plus y1 dash of n minus 1. So what is y2 of n? Y2 of n is x of n plus k1 into x of n minus 1 plus k2 into y1 dash of n minus 1 is k1 into y x of n minus 1 plus x of n minus 2. So it is x of n plus k1 into x of n minus 1, that is common, into 1 plus k2 plus k2 into x of n minus 2. Okay. Similarly, y2 dash of n is equal to k2 into y1 of n. What is y1 of n? X of n plus k1 into x of n minus 1 plus k1 into x of n minus 1 plus x of n minus 2. Okay. That is y1 dash of n minus 1. Okay. So it is a k2 into x of n plus k1 into x of n minus 1 is taken as common. So it is 1 plus k2 plus x of n minus 2. Right. So for this, we draw the lattice structure like this. So x of n, first one is x of n plus k1 into x of n minus 1. So this is k1 into x of n minus 1 into 1 plus k2 plus k2 plus k2 into x of n minus 2. k2 into x of n minus 2. These two are added so that it will become y2 of n. X of n plus k1 into x of n minus 1 into 1 plus k2 plus k2. Okay. Similarly, plus k2 into x of n. Similarly, y2 dash of n is equal to k2 into x of n, k2 into x of n plus k1 into x of n minus 1 into 1 plus k2 plus x of n minus 2, x of n minus 2. This one. So this is the two-sided or two-stage lattice structure, and this is the last one. Determine the lattice quotient corresponding to the FIR system with the system h of z is equal to 1 plus 7 by 9 into z power minus 1 plus 3 by 5 into z power minus 2 and realize it. H of z equal to 1 plus 7 by 9 into z power minus 1 plus 3 by 5 into z power minus 2. Okay. So take inverse z transform, that is x of n plus 7 by 9 into x of n minus 1 plus 3 by 5 into x of n minus 2. So for this one, we have to draw the lattice structure, two-stage lattice structure. Okay. This we are concluding the today's class. This is completed FIR filters into their structures. Okay. Yes. Okay. With this, I am concluding the today's class. Tomorrow we will start the next one. Okay. Thank you.